Okay.
Okay.
We start the final talk of this morning session. Gergely Zábrádi from Budapest, and the title is Multivariate Phi gamma modules. So please start.
Thank you. And I'd like to thank the organizers for inviting me and giving me an opportunity to give a talk here, even though virtually. But I hope next time I can travel to India. Let me, okay. Oh, it works. Sorry. So let me start with recalling some basics of Phi gamma modules in the classical sense. So the starting point is that in characteristic P, one can understand Galois representations in natural characteristic in a simple way, and this is due to Hilbert's theorem 90, because if one takes the base change to the algebraic closure of the ground field E, then any Galois representation will trivialize over E bar. So let me point out that these on the tensor product E bar with B over FP, the Galois group will act on both factors. So these are not linear representations anymore of the Galois group, but semi-linear. And any such representation will correspond to some one cocycle in the in GLM if V was in n-dimensional representation, and Hilbert's theorem 90 states that any such one cocycle is principal, so one can trivialize these representations. And up to now, this is true in any characteristic, but the additional feature in characteristic P is that one can actually recover V from D of V from this trivialized module. So the key extra structure that allows one to do this is the P Frobenius, which actually commutes with the Galois action, and the fixed field is exactly FP, regardless what your perfect field of characteristic P is. So using this Frobenius, one can recover a V from D of V. So one has this extra Frobenius action on D of V, and V can be described as the Frobenius invariant of D of V base change to E bar. However, one is interested in Galois representations of fields of characteristic 0, not just of characteristic P. So we are interested in Galois representations of p-adic fields. So one has to pass somehow from characteristic 0 to characteristic P. And classically, this is done by Fontaine and Bentham-Berger, using the field of norms functor, but this was reinvented by Scholze in a more conceptual way, and he made this notion more geometric. So for this, we need the definition of perfectoid fields. So a perfectoid field is a non-Archimedean field with some non-discrete valuation, which is complete, and the P Frobenius is onto on the ring of integers modulo P. So we call such a field with some non-discrete valuation a perfectoid field. So examples of perfectoid fields include, for instance, CP, so the completion of the algebraic closure of QP, and also the completion of QP mu P infinity, or QP adjoining the P power roots of P, or even this completed perfected closure of the Laurent series field over FP. So there are fields of characteristic 0 and the characteristic P, which are perfectoid. But for instance, QP is not a perfectoid field because the valuation in QP is not discrete. And the most important equivalence for perfectoid fields is the tilting equivalence, which allows one to translate questions in characteristic 0 perfectoid fields to characteristic P. So the tilt of a perfectoid field is another perfectoid field, which is now in characteristic P, and it is constructed as a projective limit of the field of fractions of a projective limit of the valuation ring mod P. And the projective limit is taken with respect to the P power map. So this, all this is actually due to Fontaine and Wertham-Berger. So this was called the field of norms by them, but now it is usually called the tilt of K. So and the theorem of Scholze is that the category of perfectoid extensions of K is equivalent to the category of perfectoid extensions of its tilt. The baby case of his almost purity result is that any finite separable extension is in fact a perfectoid field. So, so one can actually deduce a correspondence between finite Galois extensions of K and finite Galois extensions of K tilt. And in particular, the absolute Galois groups are isomorphic. So, so if one wants to understand the representations of the absolute Galois group of K, then then it suffices to understand the Galois representations of K tilt. And by the previous slide, we have this equivalence with phi modules for Galois representations of perfect fields of characteristic P. And another feature that follows from the functoriality of this tilting construction is that if one has a completed Galois extension of QP K, which is perfectoid, then one can actually embed the Galois group of K over QP into the automorphisms of the tilt. So this will be gamma in our case. So gamma will act on the tilt of the field. So one can use this to actually prove the equivalence between p-adic local Galois representations and phi gamma modules over perfect coefficient rings. at least. So so if one starts with a perfectoid field of characteristic 0, then of course we have this isomorphism of its absolute Galois group with the absolute Galois group of its field. So the category of mod P representations of one group is the same as the category of mod P representations of the other group, and one can understand the latter using phi modules over the tilde of k. And by taking the Witt vectors, recall that these are perfect fields. Perfectoid fields of characteristic P are in particular perfect. So one can take Witt vectors to understand p-adic Galois representations as well. But of course, one actually wants to understand representations of GQP. So and QP is not perfectoid. So one first has to pass to some perfectoid extension, and the usual choice is the p-cyclotomic extension, or actually it's completion because it has to be complete. So one takes the completion of the p-cyclotomic extension of QP, and then one gets an additional action of the group gamma, which is isomorphic to ZP cross. So this way one gets an equivalence of categories between p-adic Galois representations of QP and phi gamma modules over some field of characteristic 0 with perfect residue field. And the new feature of Scholze is that one can, in fact, construct some geometric object in characteristic P with étale fundamental group isomorphic to GQP. And for perfectoid fields, this is just the adic spectrum. But in order to introduce the action of gamma, one has to take the orbit space of the gamma action on this perfectoid space, and in the category of diamonds, there actually is a quotient space. So one can prove that this is a theorem of Scholze and Winstein that this will actually make a diamond this formal orbit space of the gamma action. However, so these are phi gamma modules with coefficient rings which are perfect, so the Frobenius is bijective on them. But for certain purposes, one needs also imperfect versions. So the baby case is that one would like to pass from the completion of the perfect closure of FP Laurent T to actually FP Laurent T, which will be the coefficient ring in characteristic P. And the observation is that actually these two fields share the same absolute Galois group. So the absolute Galois group of QP mu P infinity is not just equal to the absolute Galois group of FP of this perfectoid field in characteristic P, but also it equals the absolute Galois group of FP Laurent T. So so this actually leads to the equivalence of categories between usual phi gamma modules and mod P representations of GQP. And in this case, one needs to be careful because for perfect versions, the phi was bijective. So the phi was bijective even on phi gamma modules. But here, the bijectivity has to be replaced by the condition that the linearized map corresponding to the phi is bijective, which is equivalent to saying that in some basis the matrix of phi is invertible. And by now, most of p-adic Hodge theory can be formulated via phi gamma modules, which makes the theory of phi gamma modules even more important. But in order to recover other constructions of p-adic Hodge theory from phi gamma modules, one actually has to pass to rings of coefficients which converge p-adically at least somewhere. And the groundbreaking theorem of Charbonnier and Colmez allows one to do this in the classical situation. So this is the overconvergence of classical phi gamma modules that if one has an état phi gamma module over this completed coefficient ring, then one can descend it to a phi gamma module over the overconvergent ring. And by descending to the overconvergent ring, one can pass to the Rober ring, and from the Rober ring, it is possible to recover for instance, d de Rham, or for other representations, even decrease, or from the phi gamma module, and this is due to originally due to Berger, that one has this logarithm power series in the Rober ring. So this is the main philosophical reason why one needs to pass to the Rober ring, that one has this log of 1 plus t in that ring, and then using this little t, one can actually recover the d de Rham. And the other applications which make phi gamma modules useful use the computation of Galois cohomology and also the computation of Iwasawa cohomology by Herr's complex. So, so let me motivate why one would consider multivariate phi gamma modules instead of just classical phi gamma modules. And one of the reasons, well, the original reason for the motivation came from the p-adic Langlands correspondence of Colmez. And the observation of Colmez was that phi gamma modules are not just closely related to Galois representations, but they are also related to representations of GL2QP. So the group GL2QP has a submonoid, this mirabolic subgroup, and it's submonoid, where you take non-zero elements on the top left corner in ZP, and coefficients from ZP on the top right corner, and 1 on the bottom right and 0 on the bottom left. So this monoid actually acts on any phi gamma module. So, so the variable t in the coefficient ring corresponds to this matrix 1, 1, 0, 1, minus 1, and and phi corresponds to the matrix P0, 0, 1, and gamma corresponds to the matrix to the subgroup ZP cross 1 in the diagonal. And so any phi gamma module admits the action of such a monoid, of this non-commutative monoid, because the main observation is that gamma and phi act on the variable the same way as inside GL2P, these matrices. So on one hand, if one is given a representation of GL2QP, then one also has the action of this monoid, so one can possibly relate this to phi gamma modules. And on the other hand, if one starts with a phi gamma module, one could use some kind of induction in order to produce GL2QP representations. And if one wants to generalize this to groups of higher rank, then it is natural to expect that multivariable objects will come into the picture, because, well, even naively, the diagonal will have bigger rank. But also, a more sophisticated reason why one cannot possibly understand representations of, say, GL and QP using just representations of the absolute Galois group of QP is that on the Galois side, the p cohomological dimension of the absolute Galois group is just 2. That also follows from the Herr complex. However, on the automorphic side, we have, at least conjecturally, very complicated extensions. So, so the subtlety actually in the mod P and p-adic Langlands correspondence compared to the classical ones is that it does not suffice to understand the correspondence between irreducible objects, because the extensions are much more complicated in natural characteristics. There is a conditional theorem of Hauseux that under a conjecture of M-apton on M-apton's derived ordinary parts functor, there are higher non-vanishing extensions between certain principal series representations of GL and QP. This was also conjectured by M-apton previously. And of course, on the Galois side, since the p cohomological dimension of GQP is just 2, one cannot understand these complicated extensions just using GQP representation. And another hint on the automorphic side is by the work of Breuil-Herzig-Schraen, is that considering the Hecke isotypical components in the cohomology of certain Shimura varieties, they find that at least certain examples suggest that if there is a generalized functor from automorphic GL and QP representations, say mod P representations to mod P Galois representations, one should not get the Galois representation back using this functor, but some kind of tensor induction. And one can also ask if we can give some meaning to these factors in the tensor product. So the idea could be to just treat each tensorand as a representation of a different copy of GQP, so that on the Galois side, we have more extensions. And in order to do this, one needs a suitable notion of multivariate phi gamma modules. So let me define what kind of objects these are. So just pick a finite set, which in the applications, this delta will be the set of simple roots corresponding to the reductive group on the automorphic side. But for now, delta could be any finite set, and one takes a product of delta copies of gamma, and one takes a multivariate coefficient ring. Well, for each element in the finite set, one takes a variable T alpha, and one takes the Pyle series ring with mod p to the n coefficients, and then we invert all the variables and take the limits with respect to n. And this will be the analog of, this will be the multivariate analog of Fontaine's ring in one variable. And we consider a partial Frobenius for each variable, which behaves like a Frobenius on that variable and leaves all the other variables in it. So we have all these partial Frobeni, and we have delta copies of gamma as well, and an état phi gamma module over this ring OE delta over its mod p version is just a finitely generated module over the coefficient ring, together with commuting actions of gamma delta and commuting operators. While these operators phi alpha commute with each other and with the group action of gamma delta, such that we have this condition for each partial Frobenius. Okay, so this is the definition of an état phi gamma module over this multivariate ring, and the result is that the category of the direct product of delta copies of the absolute Galois group of QP, while the mod p representations of this direct product is equivalent to these kind of phi gamma modules, these kind of multivariate phi gamma modules, and we have a ZP and QP version of this result as well. So by now there are at least two proofs of this result. So my original proof was using just induction on the number of variables and some classical arguments of Fontaine and the praise of Colmez. But the new proof of the theorem, due to a joint work with Carter and Kedlaya, uses perfectoid spaces and making it more conceptual. And let me mention that jointly with Roy and Wei, we have a generalization to higher local fields with imperfect residue fields as well. So back to the original situation of the p-adic Langlands correspondence. So one can actually relate representations of, on the automorphic side, to these kind of multivariable phi gamma modules, via some generalization of Colmez's functor. So the main theorem is that there exists a contravariant right exact functor, well, via the previous equivalence of categories. So at first from smooth locally admissible mod p-adic representations to the category of multivariate phi-gamma modules, then using the equivalence of categories to the representations of GQP delta. So this is the direct power of delta copies of GQP. And one actually has an extra structure of an action of the center of the original group. And the properties is that this is compatible with parabolic induction, and it is the same as at least for GR2 QP. And this agrees with Colmez's functor, realizing the p-adic Langlands correspondence, and there are additional results for extensions of principal series. So so if one only considers extensions of principal series of GQP, then one even has exactness and fully faithfulness. Let me say that one does not quite get Galois representations, but projective limits of Galois representations. So these do not a priori, or they are not known to have finiteness properties. But in the case of extensions of principal series, they do. And so the ingredients in the proof are first taking some invariance. So this is a kind of Jacquet functor. So one does not take invariance under the full unipotent subgroup, but one takes invariance under this normal subgroup in the unipotent subgroup, which has zeros in the first in the second diagonal, and this has an action of a monoid, which is isomorphic to the monoid acting on multivariate phi-gamma modules. So one has an action of each copies of ZP in the second diagonal, and also the diagonal, which will give you partial Frobini and gammas, and also the center of say GR and QP. So this is in the situation of GR and QP. And for the proof of the fully faithful property, one actually needs to pass back from phi-gamma modules to representations of the reductive group via some sheaf on this flag variety, similar to Colmez's work. And let me also describe how the result on the Galois side is proven. So so the more conceptual proof due to the joint work with Carter and Kedlaya uses an analog of the cont'd formula. So recall that that Scholzer realized the absolute Galois group of QP as the état fundamental group of some diamond, and from topology one learns that if one takes the product of two pointed topological spaces, then one can describe the fundamental group of the product using the cont'd formula. And And the question is whether there is an analog of this in geometry. And in general, the answer is no, because, in geometry, this fiber product is just on the of the spectrum of two fields. It's just the spectrum of the field. So one cannot expect such a result for étale fundamental groups in general. But in characteristic P, again, the existence of Frobenius actually allows one to prove such a result. So so if one takes, so this is called Drinfield's lemma in the literature, and if one takes connected schemes of finite type over Fp and takes a direct product, then one can introduce these partial Frobeni corresponding to each component, and considering the category of finite étale covers of X equipped with commuting isomorphisms is commuting partial Frobeni, such that the composite is the Frobenius relative to X to this product. So one takes the category F étale X over phi to be the category of these finite étale maps with this extra structure. Then one actually has a Kunet formula in this situation. So the étale fundamental group of these étale covers equipped with partial Frobeni is indeed isomorphic to the product of these étale fundamental groups. And this makes it possible to actually realize the direct product of copies of GQP as some étale fundamental group of diamonds. Well, of course, one first has to generalize this theorem from schemes to diamonds, and the generalization is due to Scholze and more or less independently to Kedlaya. That Drinfield's lemma, the analog of Drinfield's lemma, actually holds for connected, quasi-compact, quasi-separated diamonds. And so one would like to use this to actually prove the equivalence of categories between multivariate phi gamma modules and representations of this direct power of Galois groups. And the technical problem is that while the diamond spectrum of QP is the quotient of some adic spectrum of some perfectoid ring, this is no longer the case for the direct power. So this is by an abuse of notation, this is not an affine diamond. So it is not the diamond spectrum of the perfect closure, completed perfect closure of our coefficient ring. So in fact, it is the rational subspace defined by the conditions that all the variables have modulus less than 1. So so in the original diamond spectrum, we also have those valuations on the ring, which allow 1 for all but 1 variables. we only have the condition that the product of the variables have modulus less than 1, not just not all of them. And so since the in this direct product is just a rational subspace in the diamond spectrum of our coefficient ring, one needs some kind of perfectoid Riemann extension theorem in order to prove the equivalence of categories. And by that, one, of course, only gets the perfect version of the equivalence of categories between phi gamma modules and the representations of products of Galois groups. And then one has to take some imperfection process. And so even though in the talk I stick to the ground field QP, it is also true for finite extensions, possibly distinct finite extensions of QP. And let me talk about the computation of the group cohomology of this product of Galois groups, a la Fontaine and Herr. So recall that in the classical situation, one can write down some explicit complex, which an explicit cochain complex, which actually computes the cohomology of the cohomology groups of GQP acting on some Galois representation. So this complex, Herr's complex, is some kind of Koszul complex for the operators phi minus 1 and gamma minus 1. That one takes, well, one of course has to introduce a sign, but these are explicitly described in terms of the phi gamma module. And one can also compute the Iwasawa cohomology using some distinguished left inverse, usually called psi, on the phi gamma module. And from the psi operator, one can construct a different complex, just taking the map psi minus the identity on the phi gamma module and computing the kernel and co-kernel of that map. And one, in order to have applications, one would like to generalize this to multivariate phi gamma modules. And okay, so of course, in our case, we have multiple Frobinii and multiple copies of gamma of ZP cross. So one of course will have a longer cochain complex computing the cohomology, and so one can if one starts with an étal phi delta gamma delta module over this multivariate coefficient ring, then one can take this Koszul complex for the operators phi minus 1 for while taking all these partial Frobinii. So this has so in degree R, one takes the delta choose R copies of D and the direct sum of those. And there is a partial Frobenius map from this to one. Well, if in degree R plus 1, the set is just one more element, has one more element in delta, then one has this phi alpha minus 1 map from one copy of the to the other, and then all the other maps are defined to be 0. So this is just the Koszul complex from commutative algebra, and And also, to compute the gamma delta cohomology, one has a similar Kosil complex. And the result with Aprameyo-Pal is that one can actually compute the Galois cohomology and the Iwasawa cohomology using these generalized Herr complexes. And the methods of the proof of this result, for Galois cohomology, one just takes some induction and a spectral sequence argument. So that's rather easy. However, for the Iwasawa cohomology, one needs to define new notions because one needs Tate duality for multivariate phi gamma modules. And one constructs a we construct a non-degenerate pairing between a multivariate phi gamma module and its Tate dual, which has these nice properties that the adjoint of the phi operator is exactly the psi operator, and these gammas are unitary with respect to this pairing, and also the action of 1 plus the variables. So this is some generalization of the usual pairing for phi gamma modules, but the problem in this multivariate situation is that this ring is not self-dual as a topological ring, and our pairing is not perfect. It is non-degenerate, but it does not give us a perfect pairing. So in order to overcome this difficulty, one needs to introduce generalizations of Colmez's lattices in phi gamma modules, and once one has the right analog of the hash mark, which is the maximal compact submodule on which the operators, all these operators psi alpha are surjective, then one can actually show that the psi complex with this D hash mark will be quasi-isomorphic to the original psi complex, and the in particular the cohomologies of the psi complex are compact because D hash mark is compact. So D is of course not compact, not even locally compact in this multivariate situation. But D hash mark is compact. So this allows one to actually prove that even though on the phi gamma modules the pairing is not perfect, this implies that on the cohomology it induces a perfect pairing. So this is the discrete side, and this is the compact side. So this actually allows one to prove that the Herr complex, the psi complex, computes the Iwasawa cohomology in this generalized situation, because one can take a Tate dual. So recall that this GQP delta is also a Poincaré group. So one has a Tate duality. And the dualizing module, which I just denote by this Tate twist. So it is mu p infinity on which all the Galois groups act via the cyclotomic character. Recall that we have delta copies of the Galois group, and each copy will act via the cyclotomic character on the dualizing module. And once you take the Pontryagin dual, then the projective limit will become inductive limit. So which can be interchanged with group cohomology, and then one can deduce the computation of the Iwasawa cohomology that way. While this is similar to the original proof of the computation of the Iwasawa cohomology, but of course we had this topological subtlety in the multivariate situation. And now I turn to the overconvergence of multivariate phi gamma modules. So to describe the overconvergence of these objects, one first has to introduce multivariate analogs of the Rober ring and multivariate analogs of the overconvergent rings. And the right definition is the naive one. So one takes the power series, which are the multivariate power series, which are convergent on some polyannuli with outer radius in each variable 1. So the outer radius is 1 in each variable, but the inner radius can vary from variable to variable. And one takes multivariate power series which are convergent on such polyannuli, and for the definition of the Rober ring, one of course takes the union of all these with respect to varying inner radii, and of course for each tuple in this interval, one has these Gauss norms on these rings, and the overconvergent rings can be defined as those power series which are bounded when the variables approach the boundary of outer radius 1. Okay, so this is in this case as well, this is equivalent to saying in the that all these coefficients are actually in the ring of integers of QP. Okay, so of course here I am considering coefficients from QP, but one could take any finite extension of QP as coefficient. And the proposition is that if one defines this overconvergent ring like this, then it actually embeds into this p-completed analog of Fontaine's ring, multivariate analog of Fontaine's ring. So this is non-trivial a priori because these overconvergent elements are not defined as having coefficients in ZP, and they are. And even the p-adic completion of the overconvergent ring equals the OE delta, the previously defined OE delta, and the result is that the base change functor from overconvergent multivariate phi gamma modules is an equivalence of categories to the multivariate phi gamma modules over this p-completed ring. And one can also compute the group cohomology and the Iwasawa cohomology using the Herr complex with coefficients in the overconvergent ring. And we have actually two proofs of this. So one is with Aprameyo-Pal, and the overconvergence in that case is proven by induction. So the overconvergence, the classical overconvergence result of Charbonnier and Colmez is just the essential surjectivity of this base change functor. which is proven in a simple induction on the number of variables. But the full property of the space change functor is a bit more subtle. So it is closely related to the computation of the Galois cohomology using the overconvergent Herr complex, because the phi gamma module morphisms from one phi gamma module to the other is just the linear maps from one to the other, which are invariant under phi and gamma. So and the home from one phi gamma module to another phi gamma module is another phi gamma module, and one has to understand the phi and gamma invariance of this home phi gamma module. In order to do so, one has to pass to either big rubber rings or the perfect versions in the joint work with Carter and Kedlaya. And the computation of the Iwasawa cohomology uses that this D hash mark is in fact overconvergent, meaning that D hash mark is contained in D dagger, which is contained in D. So one has this composite map of complexes using the psi operators, and the composite map is a quasi-isomorphism, and then one can deduce that the map on the right hand side is also a quasi-isomorphism, and since the right hand side computes the Iwasawa cohomology, so does the middle complex. And let me mention some related results. Due to Kedlaya has a version of Drimford's lemma for F isocrystals, and there are applications in the work of Brinon and Chiarolotto and Mazzari towards p-adic differential equations. So they consider multivariable Theorem representations and multivariable p-adic differential equations, and the computation of Galois cohomology using the Roba versions of these multivariate phi gamma modules is work in progress with Aprameyo Pal, and also the right analog of analytic Iwasawa cohomology. Okay, so I think my time is up. So thank you for your attention.